When we explore how modern operating systems design interfaces for creating and controlling processes, UNIX presents one of the most intriguing methods in computer science. Instead of relying on a single, straightforward system call that spins up a completely new application from scratch, it relies on a pair of distinct routines, the fork system call and the exec system call. Alongside these, a third routine known as the wait system call allows a running process to block until a process it has created completes. This separation introduces a fundamental question. What interfaces should an operating system present for process creation and control, and how should they be designed to enable powerful functionality, ease of use, and high performance? The journey begins with the fork system call, which is used to create a new process. It is certainly one of the strangest routines a developer will ever invoke. Imagine you have a running program that initiates a print statement displaying its unique process identifier, which is used in Unix systems to name and control individual processes. Immediately after, it executes the fork system call. What happens next is deeply unusual. The process that is created is an almost exact copy of the calling process itself. To the operating system, it now looks like there are two distinct copies of the exact same program running concurrently, and both copies are about to return from that very same fork system call. The newly created process is referred to as the child, while the original creator is called the parent. Crucially, the child does not start running back at the main routine. It simply comes into life inside the execution stream, as if it called the fork routine itself. However, the child is not a completely mirror image copy. While it possesses its own private copy of the memory address space, its own registers, and its own program counter, the value it returns to the caller of the fork routine is different. The parent process receives the positive process identifier of the newly created child, whereas the child process receives a return code of 0. This explicit difference makes it incredibly simple to write conditional code that handles the parent and child paths separately. Because two active processes are now competing for execution on the system, the resulting output is naturally non-deterministic. Assuming a single central processing unit for simplicity, either the child or the parent might run next. The final ordering is entirely determined by the central processing unit scheduler. Because this scheduler is highly complex, we cannot make strong assumptions about which process will execute first. To manage this non-determinism, the parent process can invoke the wait system call, or its more complete sibling waitpid. By calling wait, the parent process deliberately delays its own execution and blocks until the child process finishes executing. Once the child completes and exits, the parent unblocks, the wait routine returns, and the parent safely resumes. The final partner in this core process interface, the exec system call, which exists in several variations on Linux, such as execl, execlp, execle, execv, execvp, and execvpe. The exec routine is essential when you want to run a completely different program from the currently calling program. When a process calls a variant like execvp and passes it the name of an executable alongside arguments, the operating system reads that target binary from disk, loads its instructions and static data, and completely overwrites the current program's code segment and memory space. The heap, stack, and other memory segments are entirely reinitialized. It does not create a new process. Rather, it transforms the currently running program into a completely different running program, meaning a successful call to exec never returns. This raises an obvious question. Why build such a strange, separated interface for a task as simple as launching a program? The answer lies in the architecture of the command line shell. The separation of fork and exec allows the shell to run custom code after the fork call, but right before the exec call takes place, giving it the ability to alter the environment of the about-to-be-run program. The shell itself is merely a user program that displays a prompt, waits for a command, forks a child, alters descriptors, and executes the target program. This specific gap enables features like input-output redirection, where the shell can close standard output and open a file path, forcing any subsequent writes from the newly executed program to route transparently to a text file on disk. This exact mechanism also powers UNIX pipes via the pipe system call, which connects the standard output of one process directly to an in-kernel queue that feeds into the standard input of another process, allowing long, complex chains of command line utilities to be strung together seamlessly. Beyond these creation primitives, the operating system handles continuous management via the kill system call, which sends signals like standard interrupt or stop to halt, pause, or resume running jobs. Because unauthorized signals would compromise system security and usability, the operating system implements a strict concept of a user. Regular users can only control their own processes, while a specialized administrative account called the superuser, or root, is granted total God mode power to manage and terminate any process on the machine to maintain overall systemic stability.